Linear equations is what we have already discussed in case of polynomials in the previous session. A linear polynomial is a polynomial with degree 1, and if I have one variable, we call it as a linear polynomial in one variable. If I have two variables, then we call that as a linear polynomial in two variables. Similarly, a linear equation in two variables is an equation which is linear and consists of two variables. Say for example, I take initially with the heading linear equation in two variables. The condition here is that the equation must be linear and must consist of two variables, is what is defined as a linear equation in two variables. Say let's start with, say for example, I take 2x plus 3 equal to 0. An equation which has 2x plus 3 equal to 0 is called a linear equation because the highest power of x is 1, so it must be linear, and then it is a linear equation in one variable because I find only one unknown, which is x. Is an example of a linear equation in one variable, which is x. Is a linear equation in one variable, which is x. Similarly, if I take, say, 2x plus 3y plus 4 equal to 0, then this is called a linear equation because each of its variables have the highest powers as 1. Therefore, it must be a linear equation. But because I have two unknowns, x and y, this particular equation is called linear equation in two variables. So which differs between this and this? This is called linear equation in two variables, x and y. For example, I take x plus 3y square minus 4 equal to 0 is not a linear equation because it is linear in x, but it is not linear in y because the degree of y is 2 or the power of y is 2. So this equation is linear in x but not linear in y. Therefore, on the whole, it is not a linear equation in y because y square defines that y term is not linear. The power of y is 2. Similarly, if I take, say for example, is a linear equation because each of its powers is 1. So this is a linear equation in two variables x and y. So this is how we understand the difference between the linear equation in one variable x and linear equation in two variables x and y, is how we understand the linear equations. Now coming to the general form, how do we represent the linear equation in two variables in general form is very important of this in this topic of the session. So the general form says that a linear equation is always denoted in the form ax plus by plus c equal to 0, where a, b, c are real numbers, where a, b and c belong to R and a, b are not equal to 0, is called a linear equation in two variables x and y, is how we denote in general form. So the linear equation in two variables is ax plus by plus c equal to 0, where a, b, c are real numbers and a or b is not equal to 0. Either a or b is non-zero, is how we define the general form of a linear equation in two variables x and y. Now next the question comes on how many solutions does a linear equation have. Say for example, if I have a linear equation, I consider the power as 1. Therefore, every linear equation has only one solution. But because the linear equation here is with two variables, now the question comes, if I had a linear equation in one variable as 2x minus 4 equal to 0, then it's easy to find the solutions because immediately I can get 2x equal to 4 implies x 2 times is 2. So x is equal to 2 is the solution for a linear equation in one variable, which we obtain in this form. But how do we find the solution of the linear equations in two variables, which are the two unknowns out there, is what we are going to discuss in the continued session. Now next comes finding the solution of the linear equation in two variables. How do we find the solution of linear equation in two variables is what we are going to discuss here. So for example, let me start with the heading which says solution of linear equations in two variables x and y. Now let me take two referred examples, say x plus y plus 1 equal to 0 and x minus y plus 5 equal to 0. Now these are the two linear equations which I have here. One is x plus y plus 1 equal to 0 and x minus y plus 5 equal to 0. Now the reason why I have taken two linear equations in two variables x and y is that because each linear equation has two unknowns, we need minimum two linear equations for solving to get the solution. Getting the solution out of one linear equation in two variables is not possible because two unknowns, two conditions, three unknowns, three conditions, one unknown, one condition. So because there are two unknowns, I need two conditions out there, the condition 1 and the condition 2, which would yield finding the solution of the linear equations. Now say for example, I take these two linear equations and I wanted to find the solution, then each of them I take separately. X plus y equals minus 1 and x minus y equals minus 5. By taking all the constants to the right and all x and y terms to the left, I would like to solve using the simultaneous method. So once I just arrange all the constants on the right side and all the unknowns on the left, then I try to either add or subtract, so that on adding, we have learned about this in the lower classes. So when we add, this gets cancelled and I get x plus x is 2x minus 6. That implies my x is minus 3, which I get by solving with addition of the two equations. Now once I get the value of x, I can get the value of y either by substituting this x in this equation or this equation, depends on the choice left by you. So when I take x equal to minus 3, in one of the equation I get minus 3 plus y is equal to minus 1, which I have taken out here. This equation, which is considered here, gives me minus 3 plus y is minus 1. That implies y is minus 3 when brought to the right gets 3 minus 1, which is 2. Therefore y is equal to 2. And finally I get the solution. Therefore solution of the given linear equations is x equal to minus 3 and y equal to 2, which are the solutions of the given linear equations in two unknowns x and y, is how we solve algebraically in this method. Now as we have already discussed that every linear equation can also be represented graphically, so let's understand graphically how we can solve the two linear equations graphically. So the graphical understanding of solution of linear equations is what is for the session. Now let's see how we can find the solution of the linear equations using the graphical method. So the graphical method of finding the solutions is the session topic. Graphical method of finding the solution. Now to find the solution using the graphical method, initially let me take the similar example of the two linear equations in two unknowns x and y. So initially to start with, x plus y plus 1 equal to 0, and then x minus y plus 5 equal to 0 as two linear equations which I'm going to consider in solving them using the graphical method. Now initially to start with, as I clearly know that this is a linear equation, then this makes me understand, as we discussed in the polynomial session, that a linear polynomial is a straight line. Therefore, when I graph this on an xy real coordinate system, I get a straight line and I get a straight line, and two lines intersect. That point of intersection is nothing but the solution of the two given linear equations in two unknowns. So graphically, the solution of the two equations is the point of intersection of the two lines, line 1 and line 2. So let's draw the lines and intersect and see where the point of intersection lies. And finally, we get the solution of the given linear equations. So let's start with drawing the line for this, where I just take the table of x and y, and then I find the values for setting this as x equal to 0 and y equal to 0. Then let me find the coordinates of x and y respectively. So when x is 0, I understand this with the corresponding y being equal to 0 plus y plus 1 equal to 0 because x is 0. And then finally I get y equals minus 1. And similarly, when y is 0, I get x plus 0 plus 1 equal to 0, so that here I get x equals minus 1. So I get each of the points which relate to 0, minus 1 and 0, which when plotted on xy coordinate system and joined with a straight ruler, I get a straight line for this equation. Similarly, I take the table of values for this and then draw the straight line correspondingly for that. So let's see how the table of values would be for the second line. So taking the table with each of x and y, and then with x is 0 and y is 0, I find the corresponding x and y values respectively in the table filled up. So here when x is 0, I understand that I get the y which is equal to 5. So therefore when x is 0, my y is 5 as substituted here. And similarly, when my y is 0 equal to 0 implies x is minus 5, which I get out here. So using the two different table values which I have obtained, we are going to find the different points plotted on the straight line. So initially with this, my points are 0, minus 1 and minus 1, 0, which are the points I obtain in case of this. And in case of this, I get the points 0, 5 and minus 5, 0, which are the corresponding points which I obtain for this line. So let's initially draw a straight line joining these 2 points plotted with respective points, and then draw a straight line plotting these 2 points respectively, joining with a ruler. So let's take a real xy coordinate system. This is x-axis and this is y-axis, and this is the origin, and from where I take the straight line with points plotted. Therefore I take the scaling on x and y-axis with this starting with 1, 2, 3, 4, 5 and 6, etc., and then minus 1, minus 2, minus 3, minus 4, minus 5 and minus 6, etc., And similarly, I get here 1, 2, 3, 4, 5 and 6, etc. And then I get -1, -2, -3, -5, 4, 5, 6, all with minus signs. Then once I get all the scaling done on x and y axis, I first plot the points for the line 1 and then plot the points for the line 2. So initially, to start with, these 2 points, 0, -1 lies 0, -1 comes down because these coordinates move along y-axis and these move along x-axis. And -1, 0, so moving here, -1 and 0 comes here, and 0, -1 comes here. When I just intersect them, I get the coordinates. Similarly, I just join the points. And this is a straight line connecting x plus y plus 1 equal to 0 is the equation of this straight line. Similarly, I draw the straight line this using these 2 points, 0, 5 and -5, 0, which intersect Therefore, I get this line to be x minus y plus phi equal to 0. Therefore, these 2 lines intersect at this point, which gives me the point of intersection of the 2 lines. Therefore, the point of intersection, as we have obtained in the previous case, was 3 and 2, which I got in the case as x 2x equals -6. So x is -3 is what I obtain approximately, because I'm not using the graph paper, so I get the approximation where here the x coordinate will be -3 and my y coordinate will be -3 plus 1, which is 2, which approximately touches here. So this is the point of intersection which I obtain here, and the point of intersection decides the solution of the given linear equations. Therefore, the point of intersection is here P, which is -3, 2. Therefore, this value of x and this value of y will be nothing but the solution of the given linear equations. So for the given 2 linear equations, the x coordinate of the point of intersection, which is -3, and the y coordinate of the point of intersection, which is 2, will be the required solution of the given linear equations, is how we get the solutions. So now that we have connected the graphical method of understanding the solutions of linear equations, both algebraic and graphical method, now this makes me understand finally with my learning outcome that if I find the point of intersection, then the x coordinate of the point of intersection will be the value of x, and the y coordinate of the point of intersection will be the value of y, and which together forms the solution of the given linear equation. Now this makes me understand with different cases of the solutions. Say, for example, if the 2 lines do not intersect, then what is the status of the solutions of those 2 lines? If the 2 lines are coincident, then what is the status of the solutions of the equation? If the 2 lines intersect, then what is the status of the solution? So the different cases arise with different types of intersections, as we see in mathematics. To start with case 1, the heading is nature of solutions based on the shapes of the lines as obtained in drawing on the real xy coordinate system. Based on the trend of the lines, we can decide the nature of the solutions, which is a very important concept connecting the straight lines, the trend of straight lines with that of the solution of the linear equations. So nature of solutions starts with case 1, Say for example, if I have two lines L1 and L2 given by A1x plus B1y plus C1 equal to 0, and L2 with A2x plus B2y plus C2 equal to 0 are the two lines intersecting at one point. That implies if two lines intersect at one point, then the solution is unique in case of this kind of a trend of the two lines L1 and L2. So if I have two linear equations in two variables x and y, then we say that the solution is unique if the two lines intersect only at one point. Unique is one and only one solution. That is, we get only one value of x and one value of y in case of this kind of lines intersecting. This being the example of case 1. Similarly, I take the case 2. If I have, say, two lines which are parallel, L1 and L2 given by the similar equations, but if the two lines are parallel, where we denote with L1 parallel to L2, implies the solutions So this implies with the general understanding that the two lines never meet. When two lines are parallel, they never meet, even at infinite distance. That means when two lines do not meet, there is no point of intersection and hence no solution. That implies the two lines L1 and L2 do not intersect and hence have no solution. They do not have solution because they do not meet. No intersection, no solution is how we understand this. Now the next is case 3, where there is a possibility that the line L1 and the line L2 coincide with one over the other. So such lines are called coincident lines, where this is coincident lines. In case of coincident lines, we see that one line passes through another line. That means they both intersect at infinitely many points. They intersect. This implies the two lines intersect at infinitely many points. The lines L1 and L2 are said to be passing through each other infinitely many times, and hence mathematically they are said to be intersecting at every point. Hence they intersect at infinitely many points, and therefore we get infinitely many solutions. One intersection, one solution. No intersection, no solution. Infinitely many intersections, infinitely many solutions is how we understand the nature of solutions connected to this, this, and this. That implies infinitely many solutions is how we understand the nature of solutions connected to the graphs cut. Now, if I take the lines in general form and see how we can identify whether the two lines in the general form are intersecting, parallel, or coincident, or with unique solution, or with no solution, or with infinitely many solutions, is what we're going to discuss for the session. Say I take the two lines in general form as in the form of line L1 I take my line L1, which is A1x plus B1y plus C1 equal to 0, and my line L2 is A2x. Say for example, this is A2x plus B2y plus C2 is equal to 0. Then in this case, let's see how the different cases are derived using the coefficients. Generally here, I'm trying to connect the coefficients with nature of solutions. So the coefficients here are a1, b1, c1 for the line L1 and a2, b2, c2 for the line L2, both in linear form with two variables x and y. So let's see how we can connect the coefficients with nature of solutions. Now coming to case 1, I understand if a1 by a2, if I take here, is not equal to b1 by b2, that implies L1 intersects L2, and in turn when L1 intersects L2 I get unique solution. So implies unique solution. You can take many examples where you can verify with a1 and a2 and b1 and b2 and then divide and see. Say for example, I take x plus y plus 1 equal to 0 and x minus y plus 5 equal to 0 are the two lines, then clearly I identify here a1 is 1, b1 is 1 and c1 is 1, and here my a2 is 1, b2 is minus 1 and my c2 is 5. Then I try to simplify a1 by a2, that implies my a1 by a2 is 1 by 1, which is 1, and my b1 by b2 is clearly 1 over minus 1, which on simplification gives me minus 1. So clearly I see that 1 is not equal to 1 minus 1. That implies a1 by a2 is not equal to b1 by b2. And therefore, using the condition of a1 by a2 not equal to b1 by b2, I say that implies the lines L1, which is given by this, and L2 given by this, L1 and L2 intersect at one point, and then unique solution exists is one of the examples through which we can verify the case 1 of understanding this with algebraic approach. Now let's see the case 2 in general form, where the coefficients are connected to identifying the nature of solutions. So coming to the case 2, let's take the condition. The condition says that if a1 by a2 is equal to b1 by b2, which is not equal to c1 by c2, that implies the solution, that implies line L1 is parallel to L2 and they do not have solution. So as we already seen here, the two lines are parallel, then the two lines do not intersect and hence they have no solution. But mathematically we identify algebraically for no solution implies this is the condition which the two lines must satisfy. Let's take an example and see how we can prove the statement. Say for example, I take the two lines L1, which is x plus 2y minus 3 equal to 0, and my line L2, which is 3x plus 6y minus 18 equal to 0. Now these are the two lines which I wanted to prove with the given condition. So let's take, we clearly know that my a1 is 1 and b1 is 2 and my c1 is minus 3, and coming to the second line, my a2 is 3, b2 is 6 and c2 is negative 18. Therefore, when I just substitute in place of this, I get a1 by a2, which is 1 over 3, which is equal to b1 by b2, which is 2 by 6, which on simplification gives me, implies this is identically equal to this. And when I take c1 by c2, this is not equal to minus 3 over minus 18, because this gives me 1 by 6. Therefore, this clearly satisfies the condition a1 by a2 is equal to b1 by b2, but that is not equal to c1 by c2, which gives me 1 by 6. And they give 1 by 3 and 1 by 3. Therefore, this clearly satisfies the condition that a1 by a2 equal to b1 by b2, not equal to C1 by C2. Therefore, I can say that the lines are parallel. That implies these two lines, as given in the example problem, are parallel. That implies no solution. So this decides the factor on identifying whether the two lines are having the solution or not having the solution. So straight away with this condition, I can say the two lines have no solution because the two lines are parallel with this condition. Now coming to the case 3, let's see how the nature of solutions exist and the conditions we use for the general lines L1 and L2. So for the lines L1 and L2, in case of the third condition, I have A1 by A2 equals B1 by B2 equals C1 by C2, and in this condition we say the lines L1 and L2 are coincident for the condition this, and coincident implies infinitely many solutions because one line passes through the other line infinitely many times. Therefore, that implies there are infinitely many solutions. Many solutions is how we get the condition from the mathematical formula A1 by A2 equals B1 by B2 equals C1 by C2. So let's see this with an example problem, and just with the coincident lines we generally have, say for example the lines L1, which is x plus 2y minus 13 equal to 0 is one of the line, and the other line L2 is 13x plus 26y minus 169 equals 0. Now for these two lines, let's see if this condition is going to be a success. Now clearly from line L1, if I extract the coefficients, then I observe that A1 is 1, B1 is 2, and C1 is negative 13, as can be seen from each of the coefficients of the line L1. And then coming to the line L2, we have the three coefficients, which are A2 is 13, B2 is 26, and C2 is negative 169. And from these two conditions of A1, B1, C1 and A2, B2, C2, let's substitute in the formula of case 3. So as I see, A1 by A2 comes to be 1 over 13, and that equals B1 by B2, which is 2 over 26, and C1 by C2, which comes as negative 13 over negative 169. Now if I wanted to see if all the three constants are equal, then I clearly see that the second quantity, which can be simplified further by cancelling with 2 1s and 2 13s, and similarly I can further simplify this where 13 1s and 13 13s 169. 13 times of 13 is 169. Therefore, I clearly see here that each of the quantity reduces finally to 1 by 13, 1 by 13 and 1 by 13 after further simplifications. Now this makes me understand that this is clearly obeying the formula A1 by A2 equals B1 by B2 equals C1 by C2. Therefore, immediately I have the rule that the lines L1 and L2 are coincident, which makes me understand that these two lines are coincident and therefore they have infinitely many solutions. That implies L1 and L2 are coincident, and as you can see, when they're coincident, I have there the two lines are coincident in case of this case 3 is how I get the coincident lines. So L1 and L2 are coincident, that implies infinitely many solutions exist in case of these two lines coinciding one over the other is how I understand the case 3 connected with nature of solutions. Now let's see an example problem and find how the infinitely many solutions or unique solutions help us in connecting the linear equations or the straight lines with the nature of solutions. For example, I have a problem, say, which says for what values of p will the lines, the first line here is px plus 3y minus p minus 3 is the first line I have taken, and my second line L2 is 12x plus py minus p equal to 0, and this is equal to 0 are the two lines. Then the question here is that for what values of p will these two lines have infinitely many solutions is the question. Infinitely many solutions is the question. So here we need to find the values of p for which we have infinitely many solutions. Now, as we have seen with the case 3, this comes clearly under case 3 because if we need to have infinitely many solutions, then the two lines L1 and L2 need to coincide, passing one over the other, which is case 3 of the session which we have recently discussed on the nature of solutions. Now coming to this, let me identify A1, B1, C1 and A2, B2, C2 for each of the lines L1 and L2 and use the respective formula for case 3. Now as I clearly see here from L1, I have three different coefficients which are A1 equal to P, and then my B1 is 3 and my C1 is negative times P minus 3 are the three different coefficients of line L1, and then A2 is 12, B2 is P and C2 is minus P are the three respective coefficients of the line L2. Now for infinitely many solutions, I have the condition A1 by A2 is equal to B1 by B2 equal to C1 by C2 is the formula for infinitely many solutions. Therefore, let's substitute each of A1, B1, C1 and A2, B2, C2 in this respective formula and then identify the value of P, which is the question. So clearly I have here A1 is P, so which I'm going to substitute in place of the numerator of the first fraction P by A2, which is 12, and then I have B1 by B2, which comes as 3 by P, and then finally C1 by C2, which comes as minus P minus 3 by minus P. So I get the value of P either by choosing the pair this or this or this or vice versa. So I can choose any pair from which I can extract the value of P. So here I would like to take the pair, the first two fractions, and then find the value of P. So this being arranged as P over 12 is equal to 3 over P, which on cross multiplication would lead to P square equals 12 times 3 on the cross multiplication. That implies P square is 12 times of 3, which is 36, and therefore that implies P is plus or minus root 36, that is plus or minus 6. I get both the positive and negative value, which leads to the solution of P square equal to 36. Therefore, I have P is equal to plus or minus 6. Therefore, in order for the two lines to be infinitely many solutions, the values of P can be either 6 or minus 6. Therefore, I conclude the statement saying that depending on the question asked, therefore, for P equal to 6 and P equal to minus 6, the lines L1 and L2, which are given out here, will have infinitely many solutions. Is how we conclude the given problem. So this kind of example problems can be used for any case where if my question is for what values of P will the lines L1 and L2 have unique solution, then I use the formula for the unique solution, which is case 1 respectively, and then find the value of P respectively. Similarly, if the question says for what values of P will the lines L1 and L2 have parallel lines or have no solution, then in that case, when they have no solution, the two lines are parallel, and I use the respective condition of the case 2. A1 by A2 equal to B1 by B2 is not equal to C1 by C2. And then finally, when I simplify, I get the respective value of P. Is how we do for the 3 different cases depending on the question which demands for either case 1, case 2 or case 3. Is how we understand this nature of solutions connected with the formulae of each of the cases. Now let's see the definition of consistency and inconsistency connected with the solutions or the nature of solutions. So consistent system of linear equations is what we are going to discuss in the session. So what do you mean by the word consistent? Consistent means which has solution. Inconsistent means which has no solution. Therefore, when I say consistent system of linear equations, so let me take the lines L1 and L2. A1x plus B1y plus C1 equal to 0 and A2x plus B2y plus C2 equal to 0. Then in this case, the two lines are said to be consistent if they have solution, and are said to be inconsistent if they have no solution. Therefore, if I take the two lines, the lines L1 and L2 are consistent if they have a solution. And the solution can be either unique or infinitely many, the case 1 and case 3. So when we want to identify for the two lines to be consistent, we just identify the solutions, and if the solution is unique or infinitely many, the case 1 and case 3, then we say the system of lines are consistent. And when we identify that there is no solution for the given lines, then we say that the two lines are inconsistent, so that we get the note L1 and L2 are inconsistent if they have no solution. No solution, inconsistent. Solution, consistent, is how we make the learning outcome of this session. Now we'll see some word problems where the information is given in statements and we convert into the mathematical form, where the word problems are connected with linear equations in two variables x and y. So let's start with this example problem, which is quite interesting, and this is one of the very ancient problem in Hindu mathematics, where the Vedic mathematics, where this was really a very interesting concept utilized out there. Now, for example, here the question says, in a garden there are some bees and flowers. If one bee sits on each flower, then one bee is left over, and if two bees sit on each flower, then one flower is left over. The question here says, find the number of bees and number of flowers. Now this question has only two basic conditions given out here. The condition 1 being that one bee sits on each flower, then one bee is left, and two bees sit on each flower, then there is one flower left. And using these two conditions of the real life situation, I need to find the number of bees and number of flowers which are existing in the garden. It is quite interesting that we use mathematics to solve this puzzle. So therefore, let's see how we can connect this problem with linear equations in two variables x and y. A real life example of linear equations. So for example, I don't know the number of bees and number of flowers, so I assume them as x and y because they are unknowns which I need to find. Therefore, let number of bees in the garden be equal to some x, an unknown, and the number of flowers in the garden be y. In the garden is some y. So using these concepts of x bees and y flowers, let's see how my condition turns into a mathematical equation. Now if I read this statement very carefully, if one bee sits on each flower, then one bee is left. Therefore, say for example, I assume 5 flowers, then how many bees would be there for those 5 flowers? Because the statement says that if one bee sits on each flower, then there's one bee left. Therefore, if I have 5 flowers, there are 6 bees. Because 5 of them are already occupied on each of the flower, then there's one left. That means 5 plus 1. Similarly, if there are 10 bees, then I think if there are 10 flowers, then definitely there are 11 bees. So every time I see that the number of bees is one more than number of flowers, which says that if there are x bees, then I have the relation that x equals y plus 1. Because the number of bees is always one more than the number of flowers, as can be seen with this condition. So this is strictly because of x bees, I have one additional bee compared to the number of flowers, which is already 1, y. Therefore, I have the equation x equals y plus 1. That implies I can write this as x minus y equal to 1, or x minus y minus 1 equals 0, which is equation 1. Is the first condition I have utilized here. Now, as I see the next statement, let's see how the next statement converts to the mathematical equation. Here, I have the condition stating that if 2 bees sit on each flower, then 1 flower will be left, which makes me understand that there are 2 bees sitting on each flower, but here 1 flower will be left over. That means there's no bee sitting there. So each of x is 2y, 2 times of this. Because if I observe this statement very carefully, if 2 bees are sitting on each flower implies each bee is sitting on flower twice of y, but I have 1 flower which is left. That means I have that subtracted. If I take the number of bees is 2 times of y minus 1 with one of the flower left over, which is subtracted as 1 from this. And then finally I get here, continued with this, 2y minus 2, which on further simplification gives me x minus 2y equals minus x minus 2y plus 2 equals 0, which is equation 2. Now the question here is how to solve these two equations. We have already discussed on solving of these two equations using the simultaneous elimination method or graphical method, where we sketch the line 1 and line 2, and wherever we get the point of intersection of 2 lines is nothing but the solution of the 2 lines, which is x and y, is how we understand. So let's see how we can solve this equation 1 and 2 by elimination method. So let's see the elimination method, where I take the 2 lines. I take the line 1 below the line 2, which is given to be x minus y minus 1 equals 0, which is equation 1, and I subtract the 2 equations so that the signs change, and then this gets cancelled and I get minus 2y plus y is minus y, 2 plus 1 is 3, which is equal to 0. And therefore I get this as y equals 3. So indirectly I identify that the number of flowers are 3. There are 3 flowers in the garden. And similarly, when I substitute this y in one of the equation 1, say I substitute y equal to 3 in equation 1, then I get the value of x. As I get this, x minus 3 minus 1 equals 0, which is x minus 4 equals 0, minus 3 minus 1, and this is x equal to 4. Therefore, I get the conclusion that there are 4 bees and 3 flowers in the garden which satisfy the two conditions, the condition 1 and the condition 2 given in the statement. The condition 1 and the condition 2 given in the statement. Therefore, number of bees in the garden is 4 and number of flowers in the garden is 3, which solve the given problem. Is how we understand the linear equations in real life situations. So any problem given in the word form, we just examine that carefully, then convert that into a linear form, and then simplify and find the solutions of the two lines either by the algebraic approach or the graphical method, which we have already discussed in the previous sessions, and then finally those values of x and y will conclude the answers. Now let's see as a recap on finding the solution of linear equations, which we have seen in various methods. We have seen the elimination method and we have seen the graphical method of finding the solution of the given linear equations in two variables x and y. Now basically we have 3 different ways of finding the solution of linear equations. The solution of linear equations in x and y or in two variables is done in 3 different methods which can be used in the branch of mathematics. The first method is the substitution method, in which we substitute the value of x in y or y in x from one of the equation to the other equation, and then we reduce one of the equation into one variable and then find that variable by taking all the variables to one side and constants to the other side. So let's see in detail, but initially one of the way of finding the solution of linear equations is substitution method. Secondly, it's about elimination method, which we have already done in many of the problems. This is one of the most famous method of choosing and finding because this doesn't have any restrictions. The easiest method of all. Then finally, I have the graphical method through which I can find the solutions of linear equations. So these are the 3 methods which help us in finding the solutions of linear equations. So how do we do each one of them? Say for example, I want to use the substitution method. My step 1 is that substitute x and y, x or y from equation 1 to 2 or 2 to 1, from L1 to L2 or L2 to L1 is how we understand the substitution method. Secondly, for elimination method, we see that we make initially the coefficients of x or y to be same. So make the coefficients of x or y equal. So once we make the coefficients of x or y equal, then eliminate the equal coefficients and then eliminate by either adding or subtracting, and then we get the other equation. Is how we understand the elimination method. Thirdly, in the graphical method, we try to sketch the lines L1 and L2 and find the point of intersection. Now thirdly, for the graphical method, graph the lines L1 and L2 and then find their point of intersection. This is how we try to use the three basic methods in finding the point of intersection, or the values x and y, or the solution of linear equation. So we have the choice to use any method until and unless mentioned that this specific method has to be used. We can have the freedom of using any of the method which we have out here. But one of the most basic method is the elimination method, because this helps us in solving for any problems. So let's see each of them individually on how substitution method can be used to start with. Now let's see the substitution method in brief by taking an example problem. So initially, let me take the two lines, say my line L1, which I consider as 2x minus y minus 5 equal to 0, and my line L2, which I consider as 3x plus 2y minus 11 equal to 0. Then I wanted to find the intersection or the solution of the two lines L1 and L2. That is, indirectly I want to find the values of x and y using the substitution method. So let's see how substitution method can be used. So initially, to start with, I take each of the lines separately. My line L1, which is 2x minus y minus 5 equal to 0, and my next line L2 is 3x plus 2y minus 11 equal to 0. Now the substitution method says that we need to substitute one of the variable in the other. We have to bring in one variable into other variable form and then substitute in one of the equation. So for example, I take this being coefficient of y being 1, I always find this to be easier. Therefore, I'll bring this to the right. So I get this as y equals 2x minus 5. So in substitution method, I always suggest choose that value to be substituted which has coefficient as 1, which will always be easier. Now because the coefficient of y is 1, this is the most suitable variable which can be substituted in the other equation, making the simplification easier. This is the rule which one must follow in substitution method. So when I take y as 2x minus 5, then this is 3x plus 2y minus 11 equal to 0. Then I substitute y equal to 2x minus 5 in place of this y of the next equation. So the y which is extracted from the first line is substituted in the second line in place of that. Hence, this method is called substitution, because we are simply substituting one of the value into the other equation. So in this case, 3x plus 2 times of y, which is nothing but this, minus 11 is equal to 0. So this is how I get by substituting one of them in the other equation. Therefore, this on simplification further gives me 3x plus 2 times of 2, which is 4x, minus 2 times of 5, which is minus 10 minus 11 equals 0. Then finally, this would be 3x plus 4x, which is 7x minus 21 equals 0. Therefore, taking all x terms one side and all the constants to the other side, I get x is 21 over 7, this coming down. For the 7 1s, 7 3s. Therefore, I got x equal to 3 is the value of x. Now, once I substitute this x in this, I get y. Therefore, substituting in this equation, therefore, my y, which is 2x minus 5, will just get substituted with x equals 3, and then I get 2 times of 3 minus 5, 6 minus 5, which is 1. Therefore, y equal to 1. So x equal to 3 and y equal to 1 are the solutions of the given lines L1 and L2 using the substitution method. A substitution method which is done in this following manner. Now let's see the elimination method which can be used for the example problem which I consider. And we'll see the rules involved in the elimination method used to find the values of x and y, the solutions of the linear equations in two variables x and y. To start with an example problem, let me take the line 1 as 3x plus 2y equals minus 11 equals 0, and my line L2, which equals 2x plus 3y minus 4 equal to 0. Now these are the two lines for which I would like to find the solution using, of course, the elimination method. So in elimination method, I try to take all constants to the right so that my line L1 gets reduced to 3x plus 2y equals 11 and 2x plus 3y equals 4, as from L1 and L2 respectively. Then I use one line over the other. The next step, what I include is I take one equation over the other. So first equation is this, which I have taken. Then the next equation I take over this. Now as I see, the first rule, the most important rule in the elimination method is that the values of either x or y, that is the coefficients of x or y, must be made to be same. Now as I see here, the coefficient of x is 3 and the coefficient of x is 2, which are not equal to each other. Similarly, when I take the coefficient of y as 2 and coefficient of y as 3 are also not equal. Therefore, our attempt is to make the coefficients equal of either x or y. The choice is with the student. So let me try to make the coefficients of y as equal, as can be seen here. So to make the coefficients of y equal, what I do is I multiply this equation with this, and here I multiply with this times of 2. So the rule is we can make the two coefficients equal either of x or y. If I multiply this to the first equation and this to the second equation, finally we get a common term either for x or y, which we are going to target. Now my target here is y, therefore I have multiplied 2 to the second equation and 3 to the first equation is how I do. Similarly, when I want to make x equal, I multiply 3 to the second equation and 2 to the first equation, and then make x terms equal, or the coefficients of x equal. Now because my target here is to make the coefficients of y equal, I multiplied this 3 here and this 2 out here simultaneously, alternately, for one over the other. Now this, when multiplied, gives me 3 times of 3, which is 9x, plus 3 times of 2, which is 6y, is 3 times of 11, which is 33. So I have multiplied the constant 3 to the entire equation 1. So this forms equation 1. Similarly, I have multiplied 2 to the entire equation, second equation. So 2 times of 2x is 4x, plus 2 times of 3y is 6y, is 2 times of 4 equal to 8, which is second equation. As you can see here clearly with the two equations, I have made this equal is what is the destination. To make this equal, I have multiplied simultaneously. And this is the most important step in elimination method. Making one of the coefficients equal is a must for eliminating and finding the values of x and y. So once I make the coefficients of y as equal, then immediately I just subtract, because both plus, if I subtract, they get cancelled. So this becomes minus, this becomes minus, this becomes minus. All the signs become opposite, and then the subtraction gives me this as 0, because 6y minus 6y is 0, and 9x minus 4x is 5x. 33 minus 8 is 25 is what I get in the elimination process. The intention of making the coefficients equal is now clearly understood, because once I make the coefficients equal, when I subtract, they get cancelled and I get only one variable. This reduces to a linear equation in one variable x, which is easy to be found using the constant method. By taking the constants to the right and variables to the left, it's easy for finding the solution for linear equation in one variable. Therefore, when I proceed to the next step, 5x equal to 25 implies x is 25 over 5, which is 5. Therefore, the value of x is equal to 5. So that implies my x is 5. Now once I got the value of x, I'm going to find the value of y by substituting in one of the lines, this or this. So as I observe one thing, that my substitution of x in which equation would be easier is what I identify when I substitute. So always choose that equation which has simpler values, but do not choose an equation which has larger values, because the simplification is time consuming. Therefore, I take the easiest of these two equations, which I identify as here, because this seems to be looking quite easier. So I substitute in that equation which looks smaller. So here the equation is 2x plus 3y equal to 4, where I substitute the value of x equal to 5. So when I substitute the value of x equal to 5 plus 3y equal to 4, then 2 5 is 10 plus 3y equals 4. Then this would be 4 minus 10 is minus 6. Therefore, y is minus 6 over 3. So which clearly gives me negative 6 over 3 when 3 is brought to the right. Therefore, this would be 3 1s, 3 2s. That implies y is minus 2 and x is 5. Is how we find the values of x and y, the solutions of linear equations, by using the elimination method with all its rules out here. Now the third method is the graphical method, through which we solve the given linear equations in two variables x and y. Now the graphical method has already been discussed in the previous sessions, where the two lines are sketched on the graph, and then the two lines, when the point where they intersect, will be the point which gives us the solution. The x coordinate of the point of intersection is the x value of the solving of x and y, and the y coordinate will give us the y value of the solution of the given linear equations. So it's very simple, but we need to be very careful when we sketch, because when we draw the graph on the graph paper for the lines L1 and L2, we need to be very precise. The minute mistake might make a large difference in the values of x coordinate and the y coordinate, which we get as the point of intersection of the two lines. Therefore, the graphical method has already been discussed. Now, let's try to do one interesting problem, which is a pure application of mathematics in our everyday life. When we go to the bank, we exchange notes. We see many situations where we are puzzled, because, say for example, I go to the bank and I draw around 2000 rupees. Then the banker gives me few of the 100 rupees notes and the 500 rupees notes. Then in that case, we don't know how many 500 and how many 100 rupees notes are given, so that I get the total of 2000 rupees. So we are going to a problem where we can solve the problem of identifying the number of 100 rupees notes or the number of 500 rupees notes which are given by the banker in the total sum of 2000 rupees. So such daily life applications are various in linear equations. So many applications, through which one main application which we're going to do as an example problem. So here, let's see one of the problem which supports applications of linear equations in a pure daily life. So for example, I have a question or a problem which says, Snigdha went to a bank to draw rupees 2000. Went to bank to draw rupees 2000. She was given 25 notes of rupees 50 and rupees 100 denomination. Now here The interesting part of mathematics used is I wanted to know how many 100 rupees notes and how many 50 rupee notes did Snigdha get from the banker. In the total amount she is drawing was 2000 rupees. So the question here is how many rupee 50 notes and rupee 100 notes. So how many notes of rupees 50 and rupees 100 notes did Snigdha get from the banker is the question. Now this question is interesting because we come across such situations many a times when we go to the bank or we go to the vegetable vendors to buy some vegetables or to any other shop where we do a lot of shopping through money exchange. And therefore, we need to identify strictly its application in mathematics, especially in linear equations connected to daily life. So let's start with the clear picture of what is given. Totally, Snigdha gets 2000 rupees from the bank. She has been given 25 notes of 50 denomination and 100 denomination. Thirdly, I want to know how many 50 rupee notes and 100 rupee notes did she get from the banker. So initially, I see that total amount Snigdha draws from bank is clearly given to be rupees 2000. But the question here is we don't know how many 50 rupees notes or how many 100 rupees notes she is getting. So because we don't know the exact picture of the number of 50 and 100 rupees notes in denomination given by the banker, I assume them as X and Y, the unknowns. So here let X equal to number of rupees 50 notes as given by the banker, and let Y be the number of rupees 100 notes, denomination notes as given by the banker. So here my destination is to find X and Y, which is nothing but finding the solution of the linear equations L1 and L2. So let's see how we can frame the linear equations L1 and L2 using the minimum conditions. Now clearly, as I see here, the number of 50 rupee notes are X and number of 100 rupee notes are Y. So totally Snigdha is getting 25 notes from the banker, which clearly makes me understand that on the whole X plus Y is equal to 25, because the total number of notes, the only note she is getting is 50 denomination and 100 denomination. Therefore, the sum of these must be equal to 25, the total number of notes she is receiving by the banker. So clearly, total number of notes Snigdha gets is 25. That implies clearly X plus Y is equal to 25, which is the first linear equation in two variables X and Y I identify from the given problem. Similarly, let's see how the second equation is obtained. So as I clearly see that the total amount she is drawing is 2000 rupees. So total amount being 2000 rupees gives me the clear picture that if there are X notes of 50 rupees which she is receiving, then 50 times of X plus 100 times of Y will be equal to 2000. So therefore I get this equation because I get X is number of 50 rupees notes. So we don't know how many 50 rupees notes are there. So 50 rupee notes taken X times plus 100 rupees notes taken Y times will totally give me the total amount Snigdha is drawing from the banker. So when I add up 50X plus 100Y equal to 2000 is what I get as the second linear equation. But when I further simplify this, I divide with 50 so that I get this is what I get as the linear equation. When I divide the whole equation with 50, I get x plus 2y equals 40, which is the second linear equation. Now, once I get the two equations, solving of these two equations is a choice to the student, because the question doesn't mention about whether I had to use the substitution method or the elimination method or the graphical method. So the choice is strictly with me in the method I'm using. So clearly I identify that substitution method is very easy here because the coefficient of x or y is 1. So remember, substitution method helps only when the coefficients of x or y is 1. At least one of the coefficients of x or y is 1, unity. Now, because this clearly makes us with coefficient of y is 1, I think substitution method would be more easier in case of this example problem. So let's see how substitution method can be used to find the values of x and y. So from 1, if I just say my y is 25 minus x, because I bring x to the right, it becomes this, is what I get. And substituting this y in equation 2, then I clearly get x plus 2y. In place of y, I have this substituted. 25 minus x is equal to 40 is what I get when I substitute in place of y as 25 minus x. Now this is reduced to a linear equation in one variable x, which is very easy to simplify. So let's expand with the brackets. That implies x plus 2 times of 25, which is 50, minus 2 times of x minus 2x is 40, which on further simplification gives me x minus 2x is minus x, and 40 plus 50 comes to the right as minus 50 is what I get when I further simplify. Then finally this gets reduced to minus x equals 40 minus 50 is negative 10. Therefore, cancelling minus on both sides, I finally get x equal to 10, which in turn gives me the value of y, because when I substitute x equal to 10 here, I get the value of y. So this value, when substituted in 1, I get y equals 25 minus x, which is 10, which is 15. That implies I got the two values, one is x and one is y, which give us the answer. So therefore, when Snigdha has drawn 2000 rupees, the banker has given her 10 50 rupee notes and 15 100 rupee notes, so that when you add up, you get 2000 on the whole. So therefore, I can say, therefore, Snigdha got 10 rupee 50 notes and 15 rupee 100 notes from banker. From the banker, she got 10 50 rupee notes and 15 100 rupee notes from the banker. When she drew the total amount of 2000 rupees is how we understand the linear equations connected to the real life applications of linear equations using mathematics. Now, let's try to solve few of the linear equations which are not directly given in linear form. That is, we're going to see the session where we're going to reduce the equations into linear form. Sometimes it is essential. So let's take the topic of the day. Says equations reducible to linear form, which are not directly in the linear form. Equations reducible to linear form is what we are going to see. So let's see how the nonlinear equations are reduced to the linear form and then solved indirectly for the nonlinear equations. Sometimes it is possible. Say for example, I take the problem 2 by x plus 3 over y equals 13, and say I take the another equation 5 over x minus 4 over y equals minus 2. So these are the two equations, with the condition of course being that x and y are non-zero, because if x and y being in the denominator are zeros, the whole of the equations will not be defined. Therefore, we have non-zero solutions for this kind of an example. But initially, to start with, my question is, why are these two equations not linear? Let's recap with the definition of linear equations. As we have identified that linear equations are the polynomials, the linear polynomials whose powers are integral, non-negative integral powers. Clearly, I see that if I write this 2 by x as 2x inverse, then this is a negative integral power. The rule says non-negative integral power, which is not the case in this. Therefore, equations of this type are called non-linear equations, of course in two variables x and y. So let's see how we can convert these non-linear equations into linear form and then solve the linear form, indirectly giving us the solutions of the given non-linear equations. So the first rule for this says that if I have my equation 1 and equation 2 respectively taken for the given problem, then for the first equation and the second equation 5 by x minus 4 over y equals negative 2, I will let 1 by x is equal to some p and 1 by y is equal to some q, is how I let the two equations. So when I take 1 by x equal to p and 1 by y equal to p, implies I can write the two equations in the form 2 times 1 by x, which is p. Therefore 2 by x, which I can write it as 2 times of 1 by x, can be substituted as p, because 1 by x is assumed to be p. Therefore this equation reduces to 2p plus, similarly 3 by y can be written as 3 times of 1 by y, which is q. Therefore 3 by y can be written as 3q, which equals 13, is what we get the linear form of the equations 1 and 2. Similarly, when I take the second equation, 5 by x reduces to 5p minus 4q equals minus 2. And this would give me equation 3 and equation 4. Clearly, equation 3 and equation 4 are linear equations in two variables p and q. The variables here are assumed to be p and q, and since each of the powers of p and q are ones, which are non-negative integral powers, therefore these two equations are very much linear equations in variables p and q. So now our destination here is to solve these two equations and find the values of p and q. The method of solving can be either the substitution method or the elimination method or the graphical method. Now clearly I see that substitution method would not be an easy task because the coefficients of p and q are not 1. Therefore I try to solve this by using the elimination method, which is the most effective method of all the three methods. So in order to use the elimination method, to recap with the session, we need to make one of the coefficients equal. So let me try to make the coefficients of q to be equal, so that this is multiplied here and this is multiplied here, and I get the coefficients equal. So let's see what equations do I get when I multiply whole of equation 3 with 4 and whole of equation 4 with 3. So 4 multiplied with 2p gives me 8p, and 4 multiplied with 3q gives me 12q, and 4 multiplied with 13 gives me 52, Similarly, 3 multiplied with 5p gives me 15p, and 3 multiplied with 4q gives 12q, and therefore 3 times of minus 2, which is minus 6, clearly makes these two coefficients equal, differing by a sign, which is not a restriction. Now, since these two coefficients are equal, differing by a sign, therefore this can be eliminated or cancelled if I add, so that 8p plus 15p would give me 23p in addition, and this gets cancelled because 12q plus of minus 12q will just eliminate the q term. Is the reason why I have used the elimination method. And 52 minus 6 would give me 46, and with this I get 23p equal to 46, which in turn gives me the value of p as 46 over 23 once and twice. 23 times of 2 is 46. Therefore, I get the value of p as 2 is what I get when I substitute in elimination method. Now, the next question here is that I have to find the value of q using the value of p. So I substitute in one of the equation, which is very simple. Therefore, I substitute this in equation 4. Substituting p is equal to 2 in equation 4, I get this as 5p minus 4 times of 5 times of 2 minus 4 times of q is equal to minus 2, is what is the equation obtained with p equals to 2 substituted in the equation. Now this is 5 times of 2, 10 minus 4q is equal to minus 2, which in turn gives me minus 4q when substituted here as minus 12 is what I get out here. Therefore, the value of q here is minus 12 over minus 4, which on further simplification gives me the value as 3. Now I got the value of p is 2 and the value of q is 3, which I'm going to substitute in the assumptions, indirectly giving me the values of x and y. 1 by x equal to p, so that 1 by x equal to p, which is obtained as 2. Therefore, this implies 1 by x is 2, which on cross multiplication gives me x equal to 1 by 2. Similarly, I have 1 by y equal to q, which on substitution of the value q as obtained gives me the value of 1 by y equals 3. That implies y equals 1 by 3. So my x is 1 by 2 and y is 1 by 3 is the required solution of the non-linear equations in x and y. So a non-linear equation, when reduced to the linear form and then its solutions substituted in the assumption, indirectly gives me the solution of the non-linear equations. Thus, the topic equations reducible to linear form is possible in this manner.